down session. Second. Are you able to see my screen? You're able to see my screen, right? Hello, Kirtana? Kirtana, are you there?
Yes, ma'am.
You're able to see my
Yes,
screen,
ma'am.
right? Yeah.
Yeah, yes, ma'am.
Okay. So I welcome you for the week 8 live interactive session for the course Chemical Reaction Engineering 2. Okay. Now let's move on to the session. So as usual, we'll have a brief recap of the lectures of week 9. Okay. So week 9 had 5 lectures. Okay. The first 2 lectures of this week were on fluidized bed reactor design. Okay. It was in continuation with the last week. And in lecture 41, there was discussion on bubble diameter where Mori-Wen correlation and Werther correlation were discussed. And then how to estimate the solid velocity. So in fluidized bed reactor, you have the solid catalyst particles, right? And the solid, right? Hello? Hello, Kirtana, are you there?
Yes, ma'am.
So in a fluidized bed reactor, so there are solid catalyst particles, right?
Yes, ma'am.
Yeah. So in the difference between a packed bed and a fluidized bed reactor is that in packed bed there's a fixed packing of the catalyst particles, whereas in case of fluidized bed reactor, your solid particles are fluidized by a incoming gas flow, right? So so how to estimate the solid velocity for the fluidized bed reactor was discussed. Then material balance on gas flow and mass transfer in fluidized bed. So, there is a gas solid contact, right? So, what is the mass transfer coefficient in case of a gas and single particle was discussed. It was based on a Frost-Link correlation, and then in emulsion phase, mass transfer in emulsion phase. You remember, right? In a fluidized bed reactor, there is a bubble formation, and this bubble will have a wake, right, where more solid particles are concentrated. This is in the bottom end of the rear end of the bubble. And then this is surrounded by a cloud phase, and then further there is an emulsion phase surrounding it, right? Do you remember that?
Yes, ma'am.
Did you go through last week's lecture?
Yes, ma'am.
Yeah, so it has an emulsion phase. So the emulsion phase will have in the emulsion phase only the main reaction is going to happen. So there is a mass transfer of the reactant from the bubble to the cloud phase and then to emulsion phase, right? And then there is a mass transfer from emulsion phase to the bubble phase of the products. So what is that mass transfer and mass transfer coefficient for emulsion phase? It was given based on the Cooney-Levensbiel correlation. Okay. And then lecture 42 was further continuation on the fluidized bed reactor design, and then mass transfer in fluidized bed. So what is the mass transfer coefficient between bubble and cloud, and then between cloud and emulsion was discussed. And then reaction in fluidized bed reactor, especially the first order reaction was discussed, and an expression for height to achieve a particular desired conversion time. And also, how do you estimate the weight of the catalyst bed for weight of the catalyst for desired conversion? Were all discussed in the fluidized bed reactor design. Okay, so this completed the catalytic reactions, and then the next 3 lectures were on fluid solid non catalytic reactions. Okay, so the 3 lectures had fluid solid non catalytic reactions, and the definition for the fluid solid non catalytic reaction was discussed. So in non catalytic reaction, the solid is one of the reactants, right? The solid and a fluid will both of them will be reactants, and the product might be either only fluid or only solid or a combination of fluid and solid. Correct? That is what happens in a fluid solid non catalytic reaction. Correct? Hello?
Yes, ma'am.
Yeah. Can you just reply something if you are able to hear me or not? Because when I go to the PPT mode, no, I can't see if you are there or not. Okay.
Okay, ma'am.
Yeah. So, what are the types of products formed was discussed. Sorry. And then models for such type of reaction and examples of reaction for each model was discussed. This was followed by a discussion on progressive conversion model and the assumption and what is the concentration profile in progressive conversion model was discussed. And then lecture 44 was again continuation on fluid solid non catalytic reaction discussion. Here shrinking core model was discussed and the assumption and the concentration profile for this model was discussed. This was followed by what are the different rate controlling mechanism in a shrinking core model, and then the expression for when the diffusion through gas film is controlling the reaction in a shrinking core model was discussed. And the last lecture of the week, lecture 45, it was on fluid solid non catalytic reaction again. And then the discussion was continued on diffusion through gas film controlling the reaction, where the expression for T by tau uh, was estimated, right? Where what is tau? Do you have any idea? T is the time. What about tau? Any clue? Any clue, Kirtana? What is tau? Tau is the time for complete conversion. Okay. And then the next discussion was on diffusion through ash layer controlling the reaction. And then the expression for time for such reaction was discussed. Okay. Now let's go on to the practice assignment session. Okay. So, which of the controlling mechanisms are possible uh, uh, for a reaction rate controlling mechanism for a shrinking core model? What are the possible controlling mechanism for shrinking core model? Is it option A, diffusion through ash layer controlling, or is it option B, diffusion from bubble to emulsion phase controlling the reaction rate, or is it option C, diffusion through gas film controlling the reaction, or is it option D, diffusion from emulsion to cloud phase controlling the reaction? Which of these is applicable for shrinking core model? Do you have any clue? Just now we discussed the highlights of the lectures of this week, right? From that also you can easily identify. Any clue? You can just give any option, whichever you feel might be relevant. Kirtana, are you there? You can just unmute and speak.
Yes, ma'am, I'm here.
Yeah. You have any clue? Which are the possible, rate controlling mechanism for shrinking core model?
Diffusion through gas film controlling.
Okay. Is there anything else? Or only diffusion through gas film controlling?
Only gas film controlling.
Okay. So you're saying option C. Can we just check the answer?
Okay, ma'am.
Yeah. The answer is actually diffusion through ash layer also controlling and diffusion through gas film also controlling. Because
Okay, ma'am.
if you're just looking into the in this figure, so in shrinking core model, what will happen is that there is a solid particle. Okay, as the reaction proceeds, there will be an ash layer forming, which will be having some inerts and also products as well. Okay, so there will be a gas film followed by an ash layer and then the unreacted core. So from the given options, uh, two option can form the rate controlling mechanism. One is the diffusion through the gas film, okay, for the react for the gas phase component A to pass through, and then the diffusion through the ash also, okay.
Okay,
And
ma'am.
also there is a third possible mechanism, which is the reaction rate itself, the reaction itself, the reaction kinetics itself is controlling the rate, okay. the the intrinsic reaction itself controlling the rate, okay. So these
Okay,
are
ma'am.
the three possible mechanism in a shrinking core model, okay. Now let's move on to question number 2. Question number 2 is a problem. Do you have your calculator with you?
Yes, ma'am.
Okay. So we may have to calculate certain parameters. Okay. So let's go through the question. A pilot fluidized bed is to be used to test a chemical reaction. The bed diameter is 91.4 centimeter. You wish to process 28.3 into 10 power 3 centimeter cube of gaseous material. The average particle diameter is 100 micrometer. The reactor height is 10 feet, allowing for a disengaging height of 7 feet. This means we have a maximum bed height of 91.4 centimeter. The distributor plate is a porous disc. Okay. And what is the maximum weight of the solid hold that is held up in the bed? They have also given additional information that the pellet color is brown and the sphericity is zero point 0.7 and density of the gas phase is 1.07 into 10 power minus 3 gram per centimeter cube, and density of the solid phase, that is the catalyst, is 1.3 gram per centimeter cube, and the viscosity of the fluid is 1.5 into 10 power minus 4 poise. Okay. So what are the information given? What is it you could understand from this problem? So it's a fluidized bed reactor, correct? Hello?
Yes, ma'am.
Yeah, it's a fluidized bed reactor. That is the basic information, because in the first sentence itself they have given a pilot fluidized bed, right? They've given the bed diameter. The diameter of the bed, okay, is 91.4, and then they have to process a gas of 2.8 sorry 28.3 into 10 power 3 centimeter cube, okay. So that is the volumetric flow rate or volume of the gas that is to be processed. And then this fluidized bed is having the catalyst particle, and they have given the diameter of the catalyst particle to be 100 microns, right? That means zero point 0.1 millimeter, right? Or 0.01 centimeter, correct? And then they
Yes.
have given the total reactor height is 10 feet. And then what happens after 7 feet is that there is a disengagement, that is disengagement height. That means the bubbles and all, it will start disengaging, and then no more retaining of those things. So the actual bed height where the bed is fluidized is 91.4 centimeter, okay. And then they have given the distributor plate is a porous disc. That is, this is the disc through which your gas is going to flow, right? So there were discussion on two types of plates. One was porous plate and another was a perforated plate. So this is a porous disc, okay. And then they've asked what is the weight of the solids that is held up in the bed, okay. Now let's see how to solve this problem. So the solution scheme is as follows. So the amount of solids in the reactor is given by, you know that the amount of solid is going to be constant, whether it is going to be fixed bed or it is going to be fluidized state, right? Whether before passing the gas or after passing the gas also, only the porous, the particles are going to spread up, whereas your total weight of the solid is not going to change, correct? That is
Yes,
what
ma'am.
That is what is the case in the fluidized bed reactor. So this weight is given by, so rho C into AC into Hs into 1 minus epsilon S, that is equal to rho C AC into H into 1 minus epsilon. Correct? So what are the informations that are already available in this, from this expression? Can you just directly find out the amount of solid from this, or you need to estimate certain parameters which are, which are not available in order to substitute into this expression and find out the weight of solid? What are the parameters available? Is rho C available? Kirtana, are you there?
Yes, ma'am. Rosy is available. 1.3 is the given.
Yes, yes. What about AC?
AC
What is AC actually?
area.
Yes. Area of what?
Yes, ma'am.
Area of what? It is the area of cross section. Okay. So can
Okay,
we
ma'am.
estimate the area of cross section from the given information? Is there any information available from which area of cross section can be easily calculated? Or have
Yes,
the,
ma'am.
yeah, how do you calculate? From what information you can calculate the area of cross section?
Actually, there is a formula pi r square h for area.
Is it pi r square
From
h? Is it pi r square h or
from diameter, we can calculate the radius.
yes, okay. So which diameter you have to use? There are two diameters given in this.
Bed diameter.
Yes, correct. So from the bed diameter, you can find out the area. Right, perfect. So what about the other parameters in the expression?
The given height is 10 feet.
Is it that?
Height is 10 feet.
What is Hs? Hs is actually the settled bed height. That means before fluidizing the catalyst particles, the catalyst particle will occupy certain height in the reactor. Okay, that is what is Hs. Is that information given?
No, ma'am.
No, it's not given. Correct. So what about epsilon s? Have they given epsilon s? So they have not given epsilon s also, right? It is the porosity of the settled bed. Does settled bed before application of before passing through the gas, will it have a porosity, or it will not have any porosity? When I pack some certain solid, will it have porosity? Just imagine, you have some glass beads. Okay, you're just packing it in a measuring cylinder. Will it have porosity? Before I pass through the gas, will it have porosity? Yes, it will have porosity, right? Even if the bed is fixed also, since you are arranging multiple particles, it will have its own porosity, correct? That is why even in packed bed reactor design, you estimate the term called porosity of the bed, correct? Hello, Kirtana?
Yes, ma'am.
Yes. Are you able to get that point? That even the fixed bed will have some porosity.
Yes, ma'am.
Yes. So this is that porosity. Is that information given? No, right?
No,
So
ma'am.
that information also not given. So some height is given, whereas no information on any type of porosity is given. Correct. So now how to proceed with this? So we have to find out certain basic information like you know, your porosity of the bed under minimum fluidization, and also your fraction of reactor consisting of bubbles, because it's a fluidized bed reactor. So once you pass through the gas, there will be some formation of bubbles, right? So you have to find out what is that fraction also. Okay, so these are two basic parameters which you have to estimate. So in order to find out that, what are the parameters you need? Okay, now step 1, first, the foremost thing we have to calculate is the porosity of the bed for minimum fluidization. So the equation for porosity of the bed for minimum fluidization is 0.586 into psi power minus 0.72 multiplied by mu square by rho g into eta into dpq the whole power 0.029 into rho g by rho c power 0.021. Okay, this was the formula discussed even in the last week's lecture itself. It was discussed, right? Hello, Kirtana.
Yes, ma'am.
Yeah. So what is psi in this? Psi is the sphericity. Okay. Have they given the value of psi here? Yes, they have given the value of psi here. They have given 0.7, right?
Yes, ma'am.
Yes, they have given the psi value. What about mu? Mu also they have given 1.5 into 10 power minus 4 poise. And then the density of the gas is given. And then the diameter of the particle is also given. Correct? What is the diameter of the particle given? 100 microns, right? So
Yes, ma'am.
diameter of the particle is 100 microns. Whereas, and then you also have rho g and rho c. What about eta? What is eta? Eta is a gravitational parameter and it is given by eta is equal to your acceleration due to gravity multiplied by your density of the particles or the the solid catalyst minus the density of gas. Okay, we have those parameters as well. So now we just have to substitute the values. Eta is equal to 981 into 1.3 minus 1.07 into 10 power minus 3. Why have I, generally when we take G, we take it as 9.81, right? Hello.
Yes, ma'am. Yes, ma'am.
So why have I taken it as 981?
In terms of grams per centimeter square.
What is the unit of this acceleration due to gravity? General common, when I use it as 9.81. It is meter per second square, right? So here I have used it as centimeter per second square. That is why I have taken it as 981. And I have just taken all the terms in CGS units. Okay. That is why I have taken it as 981. Okay. And you get the eta value to be 1274 gram per centimeter square per second square. Okay. You have to be consistent in units. Okay. So these also, play a vital role, because when you just look into all these terms, it is all given in CGS units. They have given, your viscosity in poise, and then your density in gram per centimeter cube, right? Height in centimeter, volume in centimeter cube. So here everything is given in CGS units. So you have an option of either using it in CGS units itself or convert everything to SI units. Okay. Uh, by mistake, if you take your G as 9.81 and then the remaining thing in CGS units, then you will end up with a different answer, right? You will end up with 12.74 instead of 1274, correct? So you have to be consistent in units. So these small factors will cause a huge impact. Okay, so you have to just check for the units every time and make sure that all the terms in the expression, particular expression, are in same type of units, in the sense all either they are in CGS units or FPS units or it is in SI units. Okay, you have to maintain a unit consistency. Okay, okay.
Okay,
You're
ma'am.
able to get it. Yeah. Now we have all the terms for calculating your uh, porosity of the bed at minimum fluidization velocity. Correct. Now you have this expression. Can you just calculate and say what is the value of this minimum fluidization velocity? You have this expression. You have a calculator.
Yes, ma'am.
Just calculate and say what is the value of that.
Okay, ma'am.
Are you able to calculate? Kitana, are you here? Kitana?
Ma'am, it's 0.57928.
We'll just check. Yeah, it's
Yeah.
0.58. Perfect. Okay. Now
Okay.
we have the porosity at minimum fluidization. Now, as you said, we can also calculate the area of cross section of the bed, which is AC is equal to pi d square by 4. We have the value of diameter of the bed, which is 91.4. So substituting that, you get your area of cross section is 6.56 into 10 power 3 centimeter square. And then superficial velocity. Okay, so superficial velocity, you have your volumetric flow rate, that is 28.3 into 10 power 3 centimeter cube per second. Okay, uh, by AC, which is your area of cross section. Right, your volumetric flow rate by area of cross section will give you the superficial velocity, which is 4.31 centimeter per second. Okay, so these are some of the basic data. Now, the next stage, we have to calculate what is the volume fraction of the bubbles. So, the volume fraction of bubbles is given by delta is equal to U naught minus UMF by UB minus UMF into 1 plus alpha. Okay, so what is U naught? U naught is your U naught is your superficial velocity. Just now we calculated what is the superficial velocity, right? So U naught is your superficial velocity. UMF is your minimum fluidization velocity. And what about alpha? Alpha is the volume of wake per volume of bubbles, okay, which are formed because of the fluidization. As you know that when the bubbles are formed, there will be a wake area, right? So what is that volume in comparison to the volume of the bubble? That ratio is given by alpha, okay. Now we do not have the what is the value of the minimum fluidization velocity and also alpha also, right? And also ub is your bubble diameter, that is diameter of multiple bubbles. Ub naught is the diameter of single bubble, whereas ub is diameter of all the bubbles, okay. So we don't have these values, your minimum fluidization velocity, your ub and your alpha. So we have to calculate these parameters, right, in order to calculate your delta, correct. So your minimum fluidization velocity is given by psi into dp the whole square divided by 150 into mu the whole multiplied by g, which is the acceleration due to gravity, into rho c minus rho g multiplied by epsilon mf cube by 1 minus epsilon mf, right. This was also discussed in the last week's lecture itself. So we have all the parameters in this expression, correct. We have the value of your sphericity, we have the diameter of the particle, we have uh, the acceleration due to gravity, we have the density values, we have the porosity at minimum fluidization, and also the viscosity. So substituting all these terms, we get the minimum fluidization velocity to be 1.29 centimeter per second, okay. Now next, we have to calculate what is the bubble velocity. So to calculate bubble velocity, the formula is given by ub is equal to u naught minus umf plus 0.71 into g into db the whole power half, okay. So do we have all the terms in this expression? U naught is a superficial velocity. Do we have the value of superficial velocity?
Yes, ma'am.
Yes, we have the value of superficial velocity. We also have the minimum fluidization velocity. We also have the value of g. But what about dB? Do we have the value of dB? What is dB?
Bubble diameter.
Yes. Do we have the information of bubble diameter?
Yes, bubble diameter.
No, right?
No, ma'am.
Yeah. So now we have to first of all find out what is the bubble diameter. Okay. So to calculate the bubble velocity, we need the bubble diameter. So the bubble diameter can be obtained using the Mori-Wen correlation, okay, where Mori-Wen correlation is given by dBm minus dB by dBm minus dB naught is equal to exponential of minus 0.3 into h by dt, where dBm is the maximum bubble diameter and dB naught is the minimum bubble diameter, and dB is the bubble diameter. It's an average, or at a particular height what is the bubble diameter, and h is that particular height for which you're finding out the bubble diameter, and dt is nothing but your diameter of the bed, right. Now we have to find out what is the initial bubble diameter, minimum bubble diameter and the maximum bubble diameter, right, because you know to estimate the average bubble diameter. Okay, the minimum bubble diameter for a porous plate, because they have already given in the question porous plate, right. So the minimum bubble diameter is given by dB naught is equal to 0.00376 into U naught minus UMF the whole square. Okay, once you we have the value of U naught and UMF, right? So just directly substituting it, you will get the minimum bubble diameter to be 0.0343 centimeter, right? And then the maximum bubble diameter is given by dBm is equal to 0.652 into AC into U naught minus UMF power zero point 0.4 whole power 0.4. That is also it is obtained in centimeter, right. Now we have all the terms. We have the area of cross section, we have u naught, we have umf. So just substituting it, you will find out what is the maximum bubble diameter also, which you get it as 31.4 centimeter. Okay. Now, what else you need? Height of the bed. So the maximum height of the bed, they have given it as 91.4 centimeter. So at the top of the bed, what will be the bubble diameter? So will the bubble diameter vary along the length of the bed, along the height of the bed? Hello, Kirtana, are you there? Do you think the bubble diameter will vary with the height of the bed? Okay, it does vary because the expression itself has h. So as the height changes, there will be some variation in the bubble diameter, right? So at the maximum height of the bed, the diameter of the bubble is 8.86. Just substituting the height of the bed in the expression. We have all other terms calculated. So now we substitute h as 91.4 and then find out the bubble diameter to be 8.86. Whereas when the height of the at some other point at some height which is equal to half of the maximum height of the bed, what is the diameter of the bed, bubble? It will be, so h is equal to h max by 2, that is 91.4 divided by 2, so that will give you 45.7 centimeter. So substituting that, you will get a bubble diameter of 4.78 centimeter. Okay, now we have to assume this as an average bubble diameter. This is along the midpoint, right? So of the height of the bed. So based on the height of the fluidized bed. So based on that, we just take an average bubble diameter of 4.78, which we can approximate it to 5 centimeter. Okay, you're able to get this point, Kirtana?
Yes, ma'am.
You're able to get this point, right? Because along the height also there will be a variation in bubble diameter. So we just take some average. For that average, we just assume the we just consider the height as some mid height, and then substitute it in that expression and then find the diameter of the bubble and then use that diameter for further solution. Okay, now, so now with this diameter of the bubble, we can find out the bubble velocity, right? Bubble velocity ub is u naught minus umf plus 0.71 into g into dB power zero point 0.5, right? So once we substitute this, we get the bubble velocity to be 52.7 centimeter per second. Now, we have to find out what is alpha, that is volume of wake per volume of the bubble. Okay. So for that, there is a particular plot which is available in the CD content of your Elements of Chemical Reaction Engineering Fogler 4th edition. Okay, in that you have this particular figure where it gives what will be the alpha value for different diameter of the bubble. And from that, so here in this case we take it as glass spheres. Okay, and they have given the diameter of the glass spheres as 100 microns. So for that, if we just draw a straight line through this is for the glass spheres. Okay, we find out that the value of alpha closer to 0.5. So we assume the value of alpha to be 0.5. Okay, okay, are you clear with this? Can I proceed?
Yes, ma'am.
You're clear, right? We are just taking it from a particular figure, standard figure, okay, for a glass sphere, right? And then using that value for the further calculation. Okay, now, so for further solution, now we have to find out what is the volume fraction of bubbles. So volume fraction of bubbles is given by delta is equal to U naught minus UMF by UB minus UMF into 1 plus alpha. So we now have what is U naught, that is superficial velocity value we have, and then minimum fluidization velocity also we have. We have the velocity of the bubble also, and then we have the the value of the alpha also, right? So once we substitute all these values, you will get delta to be 0.06. Okay, so this is the value of delta. So fraction of cross section area filled with the solids is 1 minus delta, because delta is fraction that is filled by bubbles, because that is a volume fraction of bubbles. Delta is volume fraction of bubbles, right? So the fraction that will be filled with solid is 1 minus delta. Correct? Are you able to get that?
Yes, ma'am.
Yeah. So substituting that, we get 1 minus delta to be 0.94. Now we can find out what is the amount of solid holdup, because we have all the parameters. We have rho c we have. So because the volume and the amount of solid holdup W S is equal to rho c into AC into H into 1 minus delta into 1 minus epsilon S. Right? So here we take the height as the entire the maximum height 91.4, and then we have the cross section fraction of area that is filled by solid 1 minus delta we have, what is it, and then epsilon also we have, the porosity at minimum fluidization condition also we have. Right? Once we substitute all these into the expression, we will get the weight of solid to be 3.07 into 10 power 5 gram, which is nothing but 307 kg of solid. So that amount of solid is being used in this particular reaction. Okay, for a height of nearly 91 centimeters. Okay, okay, you got it? You are able to understand this? So in this, actually we try to calculate calculate what is the minimum fluidization velocity, porosity at minimum fluidization, and what is the bubble diameter, and what is superficial velocity, and then what is the volume fraction of bubbles, right? And all these terms we try to calculate, and finally found out what is the amount of solid holdup, right? Are you able to get this? Hello? Kirtana, are you able to get this? If you are not able to speak, can you just type in the chat box at least? Kirtana, are you there? Hello? Okay. Now, anyway, we'll just proceed with the next question. See if there is a chat box message. Okay. Now, let's go to the next question. Massimilla and Johnstone studied the catalytic oxidation of ammonia in a fluidized bed reactor. Under their experimental condition, the reaction was first order and dependent only on the ammonia concentration and without a significant change in volumetric flow rate. In one of their runs, 4 kg of catalyst was used with a gas flow rate of 818 centimeter cube per second at reaction conditions, and a conversion of 22% of the entering ammonia was obtained. Now, we have to predict this conversion using the Cooney-Levenspiel model. Okay? Kirtana, are you there? Can you just unmute and say something? Are you able to hear? Okay. So, in this particular question, they have given, this ammonia oxidation has been carried out in a fluidized bed reactor with a catalyst quantity of 4 kg and a gas flow rate of 818 centimeter cube per second, and they have obtained a conversion of 22%. This is the observed conversion rate. The 22% is the observed conversion rate. Now, they have asked us to predict this conversion using II-NPTEL model. So, they have also given some other information. Like pressure is 840 torr, that is 1.11 atmosphere. And then temperature is 523 Kelvin, which is nothing but 250 degrees centigrade. These are the operating conditions of the reactions. And then the diameter of the bed is 11.4 centimeter, and the distributor is a porous plate. Here again they have given a porous plate. This is the information on the reactor. And on the feed stream, the volumetric flow rate of the gas is 818 centimeter cube per second. And the composition is 10% of ammonia and 90% of water in the feed. And then the diameter of the particle, the catalyst particle, is 105 micrometer, which is 0.0105 centimeter. Porosity is 0.6, and then the density of the catalyst is 2.06 gram per centimeter cube, and the height of the settled bed is 38.9 centimeter. They have also given the reaction rate minus RA is equal to K into concentration of ammonia. So the reaction was observed to be first order with depending only on the ammonia concentration. That is what is given with the units of gram mole of ammonia per second centimeter cube of catalyst. And the K catalyst, that is the reaction rate constant, specific rate constant for this reaction is 0.0858 second inverse. And then the density of the gas is 7.85 into 10 power minus 4 gram per centimeter cube. And then the viscosity of the gas is 2.98 into 10 power minus 4 gram per centimeter second. And the diffusivity of A through B is 0.618 centimeter square per second. So these are the other information that they have given on operating condition, on reactor, feed stream, catalyst, reaction rate and fluid properties. Okay. Now we have to find out the conversion based on Cooney-Levenspiel model, if it is giving any similar value or completely different value to that of the observed conversion of 22%. Okay. Now, here again, we have to find out what is the gravitational parameter eta, which is equal to G into rho C minus rho G. So, we have G value 981 and rho C is also given 2.06 and rho G is 7.85 into 10 power minus 4. So, we end up with eta is equal to 2.02 into 10 power 3 gram per centimeter square second square. And then here again, the minimum fluidization velocity is to be, porosity at minimum fluidization is to be calculated. So, the same formula 0.586 into psi power minus 0.72 into mu square by rho g eta into dp cube power whole power 0.029 to rho g by rho c whole power 0.021. So, we have all the terms because they have given psi as 0.6, mu is also given as 2.98 into 10 power minus 4 and dp is also given 0.0105 centimeter and rho g and rho c are also given. So substituting all these parameters, we get your porosity at minimum fluidization as 0.657. The next is velocity at minimum fluidization. So for velocity at minimum fluidization, we have the expression psi into dp the whole square by 150 mu into the whole multiplied by g into rho c minus rho g into epsilon mf power 3 by 1 minus epsilon mf. Here again we have all the parameters and you end up with the minimum fluidization velocity as 1.48 centimeter per second, which is nothing approximately equal to 1.5 centimeter per second. Are you there, Kirtana? Are you able to follow? Kirtana? Are you able to hear me? Okay. Now here again we have to find out the cross section area of the bed. So the diameter of the bed is given as 11.4 centimeters. So from which you can find the cross section area pi d square by 4. We end up with cross section area as 102.07 centimeter square. Next is the superficial velocity. So superficial velocity u0 is given by V naught by AC. So V naught is 818 and AC is 102. So if you end up with your superficial velocity to be 8.01 centimeter per second. Now we have the superficial velocity, we have the minimum fluidization velocity. Now we have to check if this superficial velocity is in the operating range. To find out if it is in the operating range, we have to find out maximum fluidization velocity, because above maximum fluidization velocity, the particles will start flowing away from the from the fluidized bed reactor. So till the maximum fluidization velocity, the particles will stay inside the fluidized bed reactor. So in order to find out that, we have to find out what is the maximum fluidization velocity. So for this, we have the expression for maximum fluidization velocity as 1.78 into 10 power minus 2 eta square divided by rho g into mu whole power 1 by 3 into dp. So we have all the terms for this expression. So substituting all the terms, you will get the maximum fluidization velocity is 70.4 centimeter per second. So from this we can observe that the superficial velocity is well within the operating range, because the maximum fluidization velocity is 70.4, whereas your superficial velocity is 8 centimeter per second only. Okay. Now we also have to find out the Reynolds number for each case. So Reynolds number for the minimum fluidization. So the Reynolds number, the formula is I is equal to dp u rho g by mu, where dp is the particle diameter, rho g is your gas density, and mu is your gas viscosity, and u is the velocity. So for minimum fluidization velocity, your Reynolds number comes to, you have to just substitute your the velocity term only changes in these three expressions, because for minimum fluidization velocity we have to substitute that value, which is 1.5, whereas your maximum fluidization velocity is 70.4, and your u naught, your superficial velocity is 8.01. So if you find out the Reynolds number is well within the range, it is either less than 0.4 or it is between 0.4 and 500. Okay. Which are for fine particles, so which is well within the range for fine particles. Now again, here again we have to find out what is the minimum bubble diameter. So they have also given the information for porous plate. So for porous plate, as in the previous question, the expression is dB naught is equal to 0.00376 into u naught minus umf the whole square. So with which we find out the bubble diameter to be 0.16, minimum bubble diameter 0.16 centimeter, and the maximum bubble diameter is dBm is equal to 0.652 into your area of cross section multiplied by u naught minus umf the whole power 0.4, that is equal to 8.75 centimeter, sorry, 8.79 centimeter. Here again, to find out the average bubble diameter, we have the expression dBm minus dB by dBm minus dB naught is equal to exponential of minus 0.3 h by dt. So here, what is the value of h we have to substitute? They have given the settled bed height, hs is equal to 38.9, whereas they have not given any information on the fluidized bed height. So now let us assume that the expanded bed height will be 40 to 50% greater than the settled bed height. So the settled bed height is 38.9 centimeter. So we can assume the expanded bed height to be 60 centimeter, and therefore to assume an average bubble size, we are taking the height to be h by 2, that is the expanded bed height by 2, that is somewhere in the midpoint of the expanded bed height, that is 30 centimeter. Okay, this is very similar to the previous question, where also we assumed we have taken the height 50% of uh, the total expanded bed height, and then found out the average bubble diameter. So substituting that, we get the average bubble diameter to be 4.87 centimeter. Now, substituting the value of this average bubble diameter into the bubble velocity expression, we end up with bubble velocity to be 55.6 centimeter per second. Okay, here again we have to find out alpha. So, here again in this question, the diameter is 105 microns. So, in the previous question, we had the diameter to be 100 microns. So, a similar glass spheres. So, the alpha value is going to be very similar, that is 0.5. So, assuming alpha to be 0.5, now we can find out the expression for delta. So, your delta is u naught minus umf by ub minus umf into 1 plus alpha, where we end substituting all the terms, you end up with delta value to be volume fraction of bubble to be 0.122. Okay, so they have already given the mass of the bed to be 4 kg, which is nothing but 4000 grams, which is equal to rho c into ac into h into 1 minus delta into 1 minus epsilon s. Okay, substituting this all the parameters except for height, we find out the height of the bed, the expanded height of the bed to be 63.2 centimeter. So, the expanded height is 63.2 centimeter. And we assumed the expanded height of the bed to be around 60 centimeter, which is actually close to the actual, expanded height, which is 63.2 centimeter. So, we can just proceed with the assumed bed height of 60 centimeter, or we can also, take in the actual bed height of 63.2 centimeter for, further calculations. Next, in order to find out the conversion, we have to find out all the parameters related to mass transfer and reaction, right? So, the first thing to be calculated is bubble to cloud mass transfer coefficient. So, the bubble to cloud mass transfer coefficient is given by KBC is equal to 4.5 into UMF by dB plus 5.85 into DAB power half into G power 1 by 4 divided by dB power 5 by 4. So, here again they have already given the diffusivity value to be 0.61, and UMF we have calculated, dB we have calculated, G is acceleration due to gravity 981 centimeter per second square. So, substituting all these terms, we end up KBC to be, that is the bubble to cloud mass transfer coefficient to be 4.92 second inverse. Next, the cloud to immersion phase, what is the mass transfer coefficient? So, the cloud to immersion phase mass transfer coefficient is given by 6.78 into EMF. Sorry, it's actually epsilon MF. It's not EMF. It's epsilon MF into DAB into UB by dB cube the whole power half. So, we have all the terms because we have the porosity at minimum fluidization velocity is 0.657. Diffusivity we have 0.61 and UB bubble velocity we have calculated to be 55.6 and average bubble diameter to be 4.87. So, we substituting all the parameters we get the cloud to immersion mass transfer coefficient is 3 second inverse. Now, we have to, and the next step is the volume of catalyst in the bubble. So, let us assume that the volume of catalyst in the bubble, that is only in the bubble portion, is 0.01. That is, the solid occupies only 1% of the entire volume of the 1% of the bubble alone. Now, volume of catalyst in the clouds and wakes per centimeter cube of bubbles is gamma c, which is given by the expression 1 minus epsilon mf into the whole multiplied by 3 into minimum fluidization velocity divided by porosity at minimum fluidization divided by the whole divided by UB minus UMF by EMF the whole plus alpha. So, substituting all the parameters, you get the volume of catalyst in clouds and wakes per centimeter cube of bubbles to be 0.21. The next step is the volume of catalyst in the emulsion. So first we took the volume of catalyst per in the bubble, then volume of catalyst in the cloud and wake phase, and then volume of catalyst in the emulsion phase for per volume of the bubbles, per unit volume of the bubbles. So that expression is given by gamma E is equal to 1 minus EMF. EMF is nothing but your epsilon MF into 1 minus delta by delta minus gamma C minus gamma B. So we have all the terms here because delta we calculated it to be 0.122. So you get, the volume of catalyst, the fraction of volume of catalyst in the emulsion phase to be 2.25. Now the conversion is given by x is equal to 1 minus exponential of minus kr into k catalyst into h by ub, where kr is the overall coefficient and then k is your specific rate constant, which is also given, and h is the height of the bed and ub is the diameter of the bubble, and kr is given by this expression, which is kr is equal to gamma b plus 1 by k catalyst by kbc plus 1 by gamma c plus 1 by 1 by gamma e plus k catalyst by kce. So we have all the terms. So substituting everything, you will get kr to be 2.23, and then we have all other terms. So your conversion x is equal to 1 minus exponential of minus 2.23 into 0.0858, which is nothing but your k catalyst, that is your specific reaction rate constant, into 63.2, which is the actual expanded height of the column, and then divided by 55.6, which is the velocity of the bubble. So you find out the conversion to be 0.2, which is nothing but 20% conversion. So the conversion is 20% and the observed conversion is 22%. So the Cooney-Levenspiel model was able to predict very closely to the actual observed conversion for this particular reaction. Okay. Now let's go identify the identify the model and the rate controlling step from the given concentration profile. So we have been given 4 different figures of different concentration profile. So we have to find out what is the model and what is the rate controlling step for each of these concentration profile. So in the first one, hello, are you there, Kirtana? Let's move on to the question number 4. So you have seen this question, right? So you have to identify each of these figures to which model it belongs to, and what which rate controlling step is it referring to. Okay. So in the first figure, you could see the concentration along the entire radius or entire diameter, it changes with time, correct? So what model does it so these are all for gas solid non catalytic reaction. Okay. So which model does it belong to? You have any clue? You want to take a guess or shall we proceed? Kirtana, are you there?
Yes, ma'am. Some network issues. So
Okay, so you want to just try?
no idea, ma'am.
Okay. Okay. So the first one, it actually refers to progressive conversion model. So in this model, it is assumed that the reaction takes place across the entire volume of the particle. Okay. So that is why you could observe there is a concentration profile varying across the entire volume. Okay. You could see this is the original concentration. So at some time t equal to 0, this is the change, and some t1, there is a fall further, right? And at t much higher, at time much higher, there is a further fall in the concentration in the entire volume of the reactor. That is from r in the in the along the entire diameter, where this 0 represents the center of the sphere. Okay, this is the progressive conversion model. The second one, the second, third, and fourth one, as you could observe, you could see a ash layer, you could see a gas film, and an unreacted core in all these three, right? So these three are representing shrinking core model with different rate controlling steps. So in the first figure, in the figure B, you could see that the concentration of the gas is maintained till the beginning of the ash layer, whereas in the ash layer there is a drop in concentration, and as soon as it touches the unreacted core, the reaction spontaneously occurs and the concentration goes to 0. Okay, that means since the across the gas film the concentration is maintained, and similarly the reaction is spontaneous, and the concentration falls to 0 immediately. So that means it is a diffusion control in the ash layer. Okay, the ash layer is controlling the diffusion of the uh, uh, you know uh, gas A. Okay, whereas in the next case you could see there is a concentration fall in the gas film, and as soon as it touches this point the concentration falls to 0. That means the reaction takes place spontaneously. So in the gas film there is a concentration drop. That means there is a diffusion through gas film which is controlling the reaction. Whereas in the third case, what you can observe is that, so CAG is the bulk gas phase concentration. Okay, and as it reaches the gas film, there is a fall in concentration, and further once it reaches the ash layer, there is a further fall in the concentration, and once it reaches the unreacted core, the concentration drops slowly to 0. So that means the diffusion through gas is controlling, as well as diffusion through ash layer is also controlling, and the reaction is also controlling, because once it reaches the core also it's not immediately falling to 0, but it takes some span to fall to 0, right? You could just see this straight line, right, falling line, whereas in the other two cases you could just see as it touches it, it is going to 0, right? So it is controlled by all three modes of controlling mechanism. That is, diffusion through gas is also controlling, ash is also controlling, and the reaction is also controlling the uh, reaction rate mechanism. Okay. Now the final question. Sorry, not the final question. In shrinking core model for a spherical particle, the fraction of conversion is given by, what is the fraction of conversion? Is it 1 minus xb, where b is your solid particle, okay, is equal to rc by r the whole cube, where r is the total diameter of the solid particle and rc is the shrinking core diameter, sorry, shrinking core radius. Okay, or is it b 1 minus xb is equal to rc by r, or is it c 1 minus xb is equal to rc by r the whole square, or is it d 1 minus xb is equal to rc by r the whole power 0.5? So which of these is right? Do you have any clue? Do you have any clue, Kirtana? So it is actually option A. So 1 minus xb, where xb is a fractional conversion, is equal to rc by r the whole cube. Because in case of a shrinking core model for a spherical particle, uh, the expression is given by the volume of unreacted core divided by total volume of the particle, because the volume keeps on changing as the conversion proceeds or as the reaction proceeds. So which is given by, so this volume of a sphere, we know it is 4 by 3 pi r cube, right? So it is 4 by 3 pi rc cube by 4 by 3 pi r cube, where r is your uh, r is your total particle radius and rc is your shrink core radius. So that will give you rc by r the whole cube. Okay, that is the fractional conversion. Okay, whether it is going to be your gas film controlling, or is it going to be ash controlling the reaction, or the actual reaction rate controlling the reaction. Okay. The next question: in shrinking core model for a spherical particle, when the diffusion through ash layer is controlling the reaction, T by tau is given by, is it given by T by tau is equal to xb, or is it T by tau is equal to 1 minus 3 into 1 minus xb power 2 by 3 plus 2 into 1 minus xb, or is it C, T by tau that is equal to 1 minus of 1 minus xb the whole power 1 by 3, or is it D, T by tau is equal to 1 minus of 1 minus xb the whole power half? Which of these is the right option? You want to make a try?
Ma'am, I think it is third option.
Third one. Okay. Can you see the right answer? It is actually option B. Okay. Option B, T by tau is equal to 1 minus 3 into 1 minus xb power 2 by 3 plus 2 into 1 minus xb. This is the expression for when the diffusion through ash layer is controlling the reaction. Whereas your option A is when the gas film is controlling the reaction, and option C is when your reaction is the rate controlling step. Okay. And option D is for a different shape of a particle. Okay. It is for a, I think, cylindrical particle. Okay. Okay. So hope you understood the session. So that's it with the session. Okay. Thank you. You have any other doubts?
Ma'am, can you please give me the tips for final exam?
Which one? Tips?
Tips for final exam, ma'am.
Tips for final exam. This is what kind of tips you need. You have to first of all go through all the lectures completely. Okay, and try
Okay.
to solve all the problems which are solved in the class. Okay, and you have your textbook, which is the Pogler 4th edition, right? You can just try to solve those solved examples and the problems given in the end of the text also. So if you solve all those things, maybe you will be able to do it better. Okay, and just please go through the lectures. Okay, uh, and whatever doubts you have, please please upload in the forum, or you can ask in the live interactive session as well. Okay.
Okay, ma'am.
Kirtana, you got it?
Yeah, ma'am. Yes, ma'am.
Okay, 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 then that's it for the session.